Hello everyone, welcome to my channel. So this is going to be my first video of this channel and I want to start my video series on system design. So without wasting any further time, let's jump onto it. Today we are going to discuss system design on Uber. So what is Uber? Uber is basically a ride sharing app which many of us have used. If you are from India, you might have used Ola. In US, Uber is one of the most used app for ride sharing. Right. Now, the next part that we want to jump onto is functional requirements. So I have listed out a lot of functional requirements here, but I will start by marking which are the P0 requirements, which mostly we are asked to cover in an interview. So the first one is Uber app should know the driver's location who are logged in at the moment, right? So when you open the app, you do see a lot of people, all the drivers who are in your like maybe 20-mile radius or something. So this is going to be our P0 requirement. The other one is the app should be able to find the nearby available drivers. Yeah, so I think it's both the first or second requirements are similar. User should be able to request a ride, which is again a P0 requirement. At the start of the trip, the system should initiate the payment flow. We will keep it as P1 because I'm not going to discuss the payment flow, as payment flow is another topic for another video, and I'm going to cover it in the following video. The system should be able to estimate the time of arrival. This also is like a P1 for now because it involves a lot of factors, like you need to consider the traffic, you need to consider the timing of the day, duration of the day, so and it would involve some machine learning as well. So this is again going to be a separate flow. Driver should be able to confirm, yeah, this is going to be a P0. After the ride has been accepted, the driver and rider should be able to view the trip updates, correct? So we need to update in real time, right? It could be on the client side, and periodically we can send information to the server about the coordinates where the ride is with the passenger. The driver should be able to mark the ride has been completed, correct? This is going to be a P0. So all the P0s that I have marked, we are going to discuss them in this video. Non-functional requirements are availability. So obviously, if I have like let's say 10 million users using this app on a daily basis, my app should work fine. It should not go get the system down. So we need high availability. In short, scalability should also be there. Reliability, in the sense that the drivers which are nearby, it should be reliable to show the correct number of drivers. Along with that, the ride matching, plus the trip, the whole trip from the start till the end should work without any errors. Consistency. So obviously the system should be strongly consistent from one aspect. Now obviously by cap theorem, if we are targeting availability, and because it's going to be a distributed system, so it has to be fault tolerant. So we will do a trade off on consistency, but uh, Uber being a complex app, there are many aspects to it. So now in I'm talking about consistency in the terms of drivers and riders, meaning that when the rider opens the app, the number of drivers shown should be accurate. Along with that, when the trip has started, the updates that happen on the client side of the app needs to be consistent, and doesn't that we can actually do the heavy lifting on inside the app itself. And as I said, periodically we can send the updates to the backend server. So consistency in that aspect. Fraud detection, yeah, so we should be able to detect any fraudulent activity related to payments, right? So that in case like I do pay with my credit card, but let's say I don't have enough balance to pay my credit bills. The credit card company basically will reverse the payment on Uber, and Uber has to take the loss. So that is all we also need to take care of it. But again, the fraud detection part is going to be P1. We are not going to discuss P1. I'm mentioning it just in case, if in any interview this topic comes up, it's a good topic, and there are many ideas which we can do a deep dive into. So let's move on to the app usage estimation. So we are assuming that in total there are 500 million riders that use the app worldwide, and there are 5 million drivers. Like basically, 10% of the riders are drivers. And let's also give a number to DAU, which is daily active users. So we have 20 million daily active users, 2 million daily active drivers. So basically, in short, we would have 20 million daily trips, one trip per user. All active drivers send notification about their current location every 4 seconds. This is just a number. This we will be using this information to show it to our riders when they open the app, because drivers. So when drivers log into their Uber app with with saying that I'm ready to take the rides, Uber client app will start sending periodic notifications to our backend API with the XY coordinate for the driver, so that we can store it somewhere. And when the rider opens up the app using rider's X and Y coordinate, we can provide correct number of drivers in their radius. So moving on to the storage estimation. Now, for storage estimation, what all data do we need to store? So we need to store riders metadata, which is going to be the user ID, username, user email, user address. In total, one user's at data could be like 1000 bytes. So considering we have 500 million users, we'll be storing 500 GB. Now, if you see that 500 GB can easily be stored in today's servers, like one server itself is enough to store that info, right? And if we consider that we have newly how many newly registered users do we get maybe in a year, so that comes out to be 500 MB of additional data, which is nothing. So just a high level estimation would be helpful in order to help us to see that will we be spending a lot of cost in the data storage, right? um, Driver's metadata again involves driver's ID, driver's name, email, vehicle type, license number. Again, I'm assuming it's like 1000 bytes, so 5 million drivers will end up with 5 GB of total storage. Correct. And now about the driver's location metadata, which will be getting periodically. So that comes out to be around 180 MB of data, right? Now let's talk about the trip. The trip metadata will be basically user ID, driver ID, and the trip ID. These three are the fields important to us because these are primary keys for each of the tables. So if we take one row taking 100 byte, which is on a very high end. So if we have 20 million active users, the total data per day comes out to be around 2 GB, and in a year it comes around to be 1 terabyte, which is again not a huge lifting on the storage side. Now let's do a bandwidth estimation, because bandwidth estimation is important as we are using our app. We are running our app on mobile. We don't want the mobile application to get hanged or something. Mobile applications are meant to be lightweight and faster. So having a bandwidth estimation with each request would be helpful. So assuming that major bandwidth is required by location updates and the trip data being periodic information about the trip coordinates, and location updates being sent for the driver. So we have 20 million rides, and that comes out to be in a second 240 trips in a second. So how much kbps data will be sending, and it comes out to be 200 kbps of trip data that will be sending. And if we talk about driver's location, this is coming out to be 120 mbps per second, which is little bit on higher than the trip data, but yeah, it's still achievable. Now server's estimation. Now this is something which I have started doing it in my system design interviews. It does help to see how much will be a server cost, and right now we AWS, GCP, everyone, they have like this one server with this much configuration will basically cost us this much money. So if I can somehow roughly calculate how many servers do I need, so if I can calculate how many servers do I need, um, then in that case I can calculate the cost also. So basically I am assuming that each server can handle 800 requests basically in a given time, which is like in a second. So if we get 20 million requests, we would need 2500 servers. And this is and the way the way I got to this number, which is in our case 8000 requests, right? So 8000 requests, this calculation I will also cover it in another video. Here the configuration I'm consuming is RAM of uh, the machine is going to be 256 GB. That and yeah, so this, and I came up with this number. This is like an approximation, it could be more, but my understanding is if we go with this, we would need 2500 servers. I will cover this in a separate video, and we can talk about it there. Now, components involved in our design are going to be database, which stores the metadata of riders, drivers, and trips. These are the three main entities of our app. Cache, obviously, it's better to store some information in cache. CDNs effectively deliver contents to the end users. It could be about the like the driver's car, their image, their profile pic. When you open the Uber app, you do get, and those information are kind of static. They don't change that frequently. So it's better to host them on the CDNs, and we obviously need load balancers. So before we jump on to the next steps, let's go over the workflow. The way it would work is, first the driver will open our Uber app. They will send their location. Now we have a location manager service, and I will discuss this in detail. So here my plan is to basically form a kind of form a DB that involves mapping of drivers to some coordinates. So let's say if we have our Earth in a 2D frame, so I can assume that okay, at this XY coordinate, our driver is how many drivers are currently present, and I can store that value somewhere in maybe in a RAM kind of memory, because it's fast to retrieve. And then location manager can actually help us send this information to the riders app, and we will look into this in detail. Now we need driver matching. So the way it would work is, driver comes online first. They send their location to location manager. Yeah, that's it. Now rider comes and opens the app. They call an endpoint saying, "Hey, show me nearby drivers," and obviously I enter the drop off location also. So I have a ride matching service which basically calls location manager, which is going to be this location manager, and then it will send that okay, this driver is ready to accept the information. So rider is going to press the button after seeing that, oh, I can see that there are 5 drivers around my area. I will start the app. Then the request will be broadcasted to the drivers, and as soon as any one driver accepts it, the rider will be matched to it, and there will be an entry created in a MySQL DB as we want to use asset properties. So just the trip matching data, metadata is stored there, and then rider has options. If they want to cancel it, then send another flow. Otherwise it's trip started, and then the status can change to completed. Right. Now here are some APIs. Now obviously, because the interviews just stays for 1 hour, it's not good to discuss every API in depth. But just for our discussion purposes, I'm just covering all the APIs that could be involved. So one is update driver location, which I said that driver will be sending every 4 seconds. It's going to be driver ID, old latitude, old longitude, new latitude, new longitude. right? So I'll tell you why I'm sending the old latitude information also along with the client. uh, Now find nearby drivers will be an endpoint where rider will be sending their ID and their lat and long ID. Request a ride basically will give us this will happen when they click on the button that, oh, I see five drivers around me, let's request a ride. And there I'm also sharing the drop of latitude, drop of longitude, and type of vehicle, like it could be a SUV or a sedan. Now show driver ETA, this will be handled by another service, which basically based on the driver ID it gives me the ETA. Confirm pickup endpoint will be driver ID, rider IDs, timestamp is pretty straightforward. Show trip updates. This is something when the trip starts. Maybe we can set a very high what you say timeline, like every 20 seconds or every 30 seconds we'll be sharing this update just to save this on the DB. For the client side it will be happening in a very instantaneous way, but for the server we can actually have some time, because and you must also have seen that in the app, the you see the car moving after some few seconds of delay from its original position. Reason being that it's going to the backend, backend saves it and then send broadcasts everywhere to the rider and the driver also. And then there is an end trip, which is basically like the trip has ended and the status will be updated in the metadata. So this is going to be our high level design. This is going to be something like driver is connected through WebSocket servers to the location manager, and the location manager being web through WebSockets. Every 4 seconds location manager will be getting the lat long. Location manager will call quad tree map service, and I'll explain what it is. Quad tree map service is going to be our in memory database where everything is stored in RAM. Just that this is a very important point to note, right? Now what how the quad tree service works is, let me go down here and let's discuss that. So this is a very nice concept where the whole world, and just for simplicity purposes I'm just splitting this into a smaller region, but the earth can be visualized in a 2D plane, right? So if I assume that our whole earth has is on a 2D plane, and it's a matrix of 1,000 by 1,000. So I am going to split it into four quadrants, and the four quadrants being having coordinates like this, which you can easily understand. And then I will keep on splitting them, and maybe I can set a threshold saying, hey, keep on splitting the whole the node into children nodes, and there will be four children nodes till the time each node is the size of each node is maybe 20 cross 20 or maybe 10 cross 10. Like I'm basically trying to reduce the size of each node to the smallest possible value which we can get. Now the way it would work is, let's say we have four drivers on our app. What the way it would work is, they will hit the location manager. They will basically hit the location manager. The location manager will hit the quad tree map service, and the quad tree map service will try to go till the leaf node of the of the coordinates where they are, like in whichever block they are, and it will update the count of drivers there. Reason being, when the rider basically tries to hit this endpoint, basically find nearby drivers. So what it will do is, the find nearby drivers will come through the find match, and the find match will basically service will basically hit location manager. So the location manager will basically go over this tree structure, and we all know that the traverse time for a tree structure is basically log n, which is quite quick. And also, right now Uber has a mechanism where when you request a ride, it instantaneously shows the driver, so we need to be quick there. So that's why this tree data structure will help us, and it will basically try to get us as many drivers as we can. Now there is one case that we need to consider is that, what if in this one block, this leaf block, I have very less drivers. So if that's the case, I have created left and right pointers to the nearby nodes of this coordinate. Reason being that if there are less drivers, let's try to accumulate all the other children nodes which are left or right of me, and there and collect them cumulatively and then return it back to whoever requested it for. So that we can expand our region little bit and show, let's say our threshold on the app is set to, we need to show at least 5 drivers active in that region. So this pointers are going to help us in doing that. That's why and the reason being that, let's say if I hit the endpoint, I go to till this node and I return back. So if this value is very less, then we will hit the endpoint again saying, hey, give me the nearby value. So I will try traverse till this node, and then I will traverse to this node. Basically it's going to be log n plus log n plus log n. This is much better that I have a log n traversal induced, and then I have in kind of close to O of 1 time I'm getting the neighboring values also, and then sending it back to to the riders API basically. So this is what is happening here. Now once the nearby drivers is visible, rider is happy that there are some drivers in my region. The rider will click on the request find match button basically. Now what Uber has done is they have started a timer kind of thing where, like, I think for 2 or 3 minutes it shows you in the app, hey, we are trying to find a match. Reason being, they're trying to leverage this 2 minute or 3 minute latency to basically send request, broadcast request to all the drivers in that coordinate area. So there are things that happen here when you click on the request vehicle. When you click on the request vehicle, find match service is going to hit location manager saying, hey, just broadcast that there is a rider with this latitude and longitude, and this is the drop off latitude longitude through WebSocket, because it's WebSockets are duplex connections. All the drivers in that region will get a notification, hey, do you want to accept this ride? As soon as one of them accepts it through WebSocket, it basically returns back to the find match. The find match that sends to the request vehicle, hey, this thing ride has been accepted, and the find match basically creates a entry in the database as well, which is going to be MySQL in our case. And then yeah, and the rider sees that, oh, this request has been accepted. Now we can start the trip. So now what happens is this another flow gets triggered in the meantime when the find match has been accepted, because here the driver gets the first authority to basically accept it or not. Rider doesn't have any kind of authority that, oh, I want to go with this driver or I want to go with that driver, right? So basically for driver, from the rider's perspective, it's basically as soon as they click on the request vehicle button, after 2 minutes they are just gonna see who is their driver. But in the meantime, what all has happened is we have created a entry in DB, and through the location manager has basically triggered an endpoint to the ETA service. And then in the ETA service, it has loaded that this is the driver's location. Now ETA service is a complex service, all the computation is happening, and the request vehicle basically now hits the ATA service to get that information that, oh, how much time is it gonna take for this driver to come to me. That's all. So it's basically talking to ETA service and getting the information about it. Yeah, all these workflows, I have done some detailing here. What I'm going to do is, I have already spoken about it. I am going to share the link to my Medium article also, where we have all this information, and then you can go over the stats and the calculations that I've done, right? And here is the schema of how the database will be look, and we'll be using NoSQL and MySQL. MySQL is basically to store data about driver and rider, and also the trip status status will be updated, because we want consistent status update across the whole application. And we are ready to do a trade-off between the latency, that okay, even if it takes some time to update the status correctly, it's fine, we need the correct status. For NoSQL, we can use it for location basis, the route information, payment information, because NoSQL is quick, and like if we use DynamoDB kind of a structure, it's read and write heavy both, so that is helpful. uh, ETA service, I've just talked briefly here. In a rudimentary implementation, we can use Dijkstra's to find the smallest route between route driver and the pickup person. Reason being, we already would have the whole map coordinates with us, right? And we would have driver's information and we would have the rider's information, so we can easily run Dijkstra's to get the information how much time is going to take. Obviously, it's not considering the speed limit of on the edge, the time of the day, and the crossings, and on the traffic also. So these four factors are not involved yet. The easiest way would be we can use Google Maps API, which does give us very accurate information how much time is going to take. So we can use that all together, or we can use these constraints and implement our own structure, right? Of payment structure, for payment service, there are two ways. One is you implement in-house solution, the other is you use a third party integration like Stripe, which takes care of everything, right? Now, there is one more thing that I do after discussing the high level overview and the schema API design. I always go over whether whether my requirements have been achieved or not. So in the initial stage, in the non-functional requirements, we said that we want availability. So obviously that could be taken care if we have server replicas and load balancer. We have replicas for a database, and yeah, server failures can be hidden from the end users as well. Scalability is there because we are using NoSQL database and we are having a distributed structure, like having more servers with load balancers. No single point of failure, right? If any one, let's say find match has four servers. If one server goes down, it's fine. We have other three to take care of it. Strong consistency, in this case, I again said that because of cap theorem, we would take a hit on consistency, but we are doing a trade-off between latency, which is like we are ready to take as much time as we want just to update the trip status, which is being the first time the match happens and the trip status is started. Then later on, if it's cancelled or if it's completed, that information is stored in a SQL database. Reasons being, it provides us with asset transactions. So I think that's all I wanted to cover. I know I did a lot of overview rather than going in depth for many things. This was the reason being, I I wanted to go over the way I approach it in interview. An interview is for 1 hour, and you cannot actually design the real Uber in that 1 hour, right? I'm going to add all these details to my Medium article so that you guys can go ahead and read it offline. And if you guys like this video, please like and subscribe my channel. That will help me and support my channel, and I can create more videos around this. Thanks everyone.